It's working.
Welcome to the third day of the ASI meeting. I hope your stay was comfortable so far and you are enjoying the meeting. So now we have the third plenary session as well. We have wonderful lecture in this particular session. The first talk by Rajaguru. We'll be talking about solar interior dynamics and helioseismology.
Okay, yeah. Can you all hear me? Okay. Yeah, it's working. Okay, good morning everyone. Let me start with thanking the SOC for giving me this opportunity to give an invited talk here. So I'm from the Indian Institute of Astrophysics in Bangalore. I'll be talking about solar interior dynamics and helioseismology. It's a very fairly general topic, but I will not be able to cover all of it. As I will go along, I will introduce what I will be talking about. Before I go ahead further, let me acknowledge collaborations, my collaborators, my student at IIA and Antia. He's retired from TIFR. He's now at the University of Mumbai, and also the collaborators, my helioseismology team at Stanford University. Okay. So let me introduce what solar interior dynamics, what I'm going to talk about. So what is shown here is kind of cartoon depiction of the plot in the middle is the real observation from helioseismology. What I am explaining here is the major flows which we know exist in the sun. There is a differential rotation which is very well measured on the surface. It is also helioseismology has measured throughout the sun, most reliable in the convection zone of the sun. So the convection is in the outer 30% of the sun, which you all know, and then the differential rotation, and there is this meridional circulation which is depicted here on the right. If you can see, there is a closed streamlines here depicting a single cell of circulation inside the sun. This is called the meridional circulation, which is very well observed on the surface, which you can directly measure on the surface, which is of the order of 15 meters per second at the surface. On the other hand, the rotation is, as you all know, it's about 2 kilometers per second. It's a very compared to the meridional flow, the rotation is a very much faster flow. So because of that, because it is so small amplitude here in the surface, it's very, very difficult to measure in the deeper inside the sun. So we really don't know what the structure of the meridional circulation is inside the sun. So the fluid dynamics of the solar convection zone is coupled, all these motions, rotation, convection, and meridional circulation. All of that should come out as a solution to your fluid dynamic equations. There are very different kinds of simulations, theoretical models. None of them actually reproduce all the observations what we have right now, except the meridional circulation is not very well measured. Let me start with this movie. So why is the solar interior dynamics so important is to explain what we observe here on the surface. This is the so-called magnetograms measured over several cycles and made as a movie. What you see here is the two colors are the two polarities of the magnetic field, basically the active regions on the sun over time, how they appear and disappear, forming the solar cycle every 11 years. So this solar cycle is controlled by what I explained in the first slide, the interior dynamics. So although we have been observing this for centuries now, this sunspot observation have been going on from Galileo's time. We still don't have a theory which can explain what we observe, the solar dynamo, the magnetic fields. Okay, so this is did I miss? Okay, so So this is the so-called magnetic butterfly diagram. If you just plot as a function of time and latitude, sine of latitude, you see this butterfly-like structure. What one can easily observe that there is this transport of magnetic flux on the surface. So the two colors are the two polarities of the magnetic field. You can see the alternating change of sign in the polar magnetic field, which is basically due to the sunspots appearing over a solar cycle and the following polarity magnetic field of the in a particular hemisphere gets advected to the poles, and you form this alternating pattern of magnetic field near the poles. This defines this LO to another LO. It takes 22 years. That's the magnetic cycle of the sun. So this is the same thing plotted in a different way, the area of the sunspots. This is, as I said, this has been observed from Galileo's time. The very long-term observations exist. So we recently, just a small aside, we recently, talking about long-term magnetic field, we have the Kodaikanal Solar Observatory, which has been observing the sun for more than a century now. We had a meeting last month to celebrate 125 years of Kodaikanal Solar Observatory. There was a large gathering of international solar physicists, international scientists from all over the world. So one of the reasons for a thin audience here from solar physics faculty level is probably because they were very tired of attending this meeting after just a month ago. Okay, so sorry, there is a. Oh, okay. All right. So other aspects of interior dynamics or the near surface dynamics is the sunspots. I won't be talking much about this, but I just wanted to say this for completeness. So there are also flows around active regions, which are the active regions which appear and go and appear and decay. There is a large scale flow pattern observed around them, which is which also couples to the other flow structures which I just talked about. One of the major unsolved problem is how these flows around active regions couple to the large scale rotation and convection. I thought I would just flash some cartoons on this. So I won't be talking much about this. In the later part of the talk, I will briefly mention one of the projects which I am working on. Okay, so let me introduce helioseismology. Helioseismology is study of solar oscillations. Sun, as you can see in this movie, sorry. So sun oscillates in a very well-defined set of oscillations, which is shown in this movie. Okay, anyway. So this is the depiction of the Doppler observation which we can observe. This is from space, from the instruments called HMI and Solar Dynamics Observatory. So the sun, the oscillations were first discovered in the 60s, and they have been very, very well measured. Now the global helioseismology involves studying these oscillations in terms of spherical harmonics, in terms of the wave number, spherical harmonic degree L, and the radial order n, and then of course the frequencies of these normal mode oscillations. So this helioseismology, the use of these oscillations to study the interior structure of the sun has been very well developed. We know the interior structure of the sun very well to a very, very high accuracy, except in the core. But what is not very well understood, what is not very well measured is the dynamics, which I just talked about. Okay, I will skip this. Okay, so just a quick introduction. So how do we measure the solar oscillations? So usually through the Doppler shift, you measure the Doppler shift of the spectral line, which is forming in the photosphere. You make a Dopplergram, which is shown here, and you typically subtract all the motions like due to rotation and convection by simply averaging a large number of images. You observe every 1 minute or so. here 45-second observations. If you typically subtract, say, 1 hour of observations, then what is you subtract them from each observation, what is left out is the solar oscillation. And you can measure them. And the way global helioseismology is done is that you take a spherical harmonic transform of this and get a time series and make a power spectrum, and then you plot a power spectrum as a function of L and the frequency. And the oscillation frequencies can be measured this way, and that's what they are used in concerning the structure. So the main facilities which we have for observing solar oscillations are listed here. There is a GONG instrument, Global Oscillation Network Group, which has been observing the sun from 1995 onwards, more than 2 solar cycles long now. And there are 2 key space instruments. One was on SOHO, and another one on Solar Dynamics Observatory, which was launched in 2010. And these HMI is currently producing data. Most of the results which I talk about is based on this instrument. Okay, so let me give you a brief introduction to the solar interior rotation, which is the very well measured solar. For example, this. This basically involves measuring the oscillation frequencies, and then because of the rotation, there is a degeneracy is lifted. The modes which are propagating in eastward and the westward have slightly different frequencies. You can measure those frequency shifts. Those are written in terms of splitting coefficient, and one can invert the splitting coefficients to derive the rotation. This is an integral equation which relates the frequency shifts to the interior rotation. This is one of the results that probably is taken from Antia and Basu. So this is very well determined interior rotation shown here. What you can easily notice here is the differential rotation over latitude, and there is also near the surface and near the 0.7 solar radius, near the base of the convection zone, there are 2 strong shear layers. Strong shear appears. These 2 layers are thought to be very, very important for what I mentioned about the operation of the solar dynamo. Let me go ahead. So this is another picture of depicting the same. This is one quadrant of the solar interior, and this tachocline, the shear layer near the base of the convection zone is called the tachocline, and the one near the surface is called the near surface shear layer. Later I will show some results on this, which I have been doing, working on with several collaborators. Okay, so let me first talk about the meridional flow, which I have been spending a lot of time over the last 10 years or so. So the meridional flow, as I said, it's a flow which is very well observed on the surface. The very first observations came in the late 70s and later from direct Doppler observations. And you can also track the features. One of the magnetic butterfly diagram which I showed you, there you see the magnetic field slowly getting advected to the poles. You can track those features, and you can also measure the meridional flow. And later in 2010 or so, there was this local helioseismology techniques which were applied to measure these small flows. So the global frequencies, when you measure, they are shifted by the small scale flow, these small amplitude flows to a very, very small amount. It's very, very difficult to measure them. So you need to apply a technique called local helioseismology, which was very first observed, applied by Basu and Antia to study the meridional flows. So what is shown here is as a function of latitude and the meridional flow in the y-axis measured over different years, and this is one of the early measurements of meridional flow, which only shows you how the meridional flow looks at the surface. Okay, so talking about local helioseismology, what we do is you take a small area on the sun. These are the Doppler observation which you see. You can study the waves locally, and that way you can measure the local flows more accurately. So what you need to do is there are two different techniques. One is called the time distance helioseismology, where you can correlate 2 points in this Doppler field, 2 points separated by a distance, and you do a time correlation, temporal cross correlation, and you can measure travel times as a function of distance. And that is what I use most of the time to study this meridional flow. And there is another technique called ring diagrams, which is which was used by Basu and Antia to measure the surface meridional flow. Okay, so I will skip this. We'll come back to it. So one of the very first observations to use this time distance helioseismology to measure the slightly deeper meridional flow was by Peter Giles and Tom Duval in 1997. It was published in Nature. This was the very first observation of slightly deeper extending meridional flow from time distance helioseismology. So they found that from equator to poles, up to about 40 to 60 megameters, there is a flow. This is in terms of travel time shifts of the waves, acoustic waves, which trace the flow. You can invert this travel times to find the flow. What they found was that up to about 40 megameter below the surface, there is a poleward flow. So there was a very first detection slightly to deeper layers. Okay, so later, after the STO Solar Dynamics Observatory was launched, so up to then, going deeper than 40 megameter was very difficult. We could not measure the travel times accurately to measure the small flows deeper than 40 megameter. But around 2012, after STO was launched, the group at Stanford discovered something called center to limb systematics in the measurement of travel times. When you measure travel times for waves, for example, here these are the travel times depicted as a function of the full surface of the sun. You see the dipole-like structure. This basically corresponds to the flow which is going from the equator to the poles. What they discovered, what Junwei Zhou and others discovered, was that when you use different observables to measure these flows, they found different signals. Okay, here it is as a function of longitude. So that if you use continuum intensities of the particular spectral line near the spectral line, and if you use those intensities to measure travel times, and you can also use the Doppler velocity to measure the travel times, they don't agree. There is a very widely differing measurement for the meridional flow. So, so then they discovered that if you measure, this is for the north-south, if you measure on the east-west direction, you also see the same dipole-like signal. So, which is, there is no flow from the central meridian to towards the limb on both hemispheres. That is an artifact. So, if you remove this artifact from this measurements, all of the measurements match. So, this was an important discovery that measuring travel times is subject to this center to limb systematics. If you remove it, you are able to better constrain the meridional flow. So, after applying this, the team at Stanford found that this particular result, which is the, as you can see here, what is plotted here is the inverted flow velocities. Red is about 15 per meter per second, blue is minus 15 meter per second. What they discovered was that there is this red changes into blue at around 0.9. 0.9 is about 60 megameter below the surface, or little more than that. So they found this double cell structure. After improving the measurements, they found that the meridional circulation is actually in 2 cells. Okay, so that was a big surprise. Because if you apply that measurement in the dynamo models, the so-called flux transport dynamo models, which the best model which we have, which fails, which is you cannot have 2 cells in depth in the convection zone, and still you can you cannot reproduce the butterfly diagram from the dynamo model, which otherwise works for a single cell. So what we attempted to do this independently. I formed a team with Antia in 2015. We measured, we used the same data, little longer data. We used additional constraints while doing the inversions. We implemented the mass conservation. Then we found that the measurements actually give a single cell, as you expect, to match with what dynamo theory requires. So this was published in 2015, but then there was several other teams which worked on this problem, and there was no agreement between. This is a summary of all the measurements which have been carried out so far. There are double cell results. As you can see, there are two teams, the Stanford team and the Gong team, Jakiewicz et al. The top two left panels show, and also the another later measurements by the Stanford team, much improved measurement, they still claimed that there is a double cell. But the latest result in this field is by Gison et al. It was published in 2020, and they used two full solar cycles for data from Gong and MDI combined, and they found a single cell. So there is still, the jury is still not, there is no still confirmation that the other teams can reproduce this. So there is still a disagreement among researchers about what really is the structure of the meridional flow deeper in the interior. So we have formed at least 3 of these teams, except the team which produced the single cell. All of us are together now to exchanging our measurements to really find out what is really going on. I will skip this. So this is again what I just explained. There is this 2 measurements, ours and the latest measurements find a single cell circulation. I'll skip this. So one more problem in this, that whether these results are trustable or not, again came from my own finding that in 2020, around the time they published the single cell results in Science, I noticed that the systematics which you remove to make a better measurement of interior is actually problematic. If you use different frequencies of the solar oscillations to measure this, so you get 2 different results. So there is at 3 millihertz, as you all know, the solar oscillation varies from about 1.5 millihertz to 5 millihertz, the standard normal modes. If you use different bands of frequencies to measure this, the meridional circulation, I found that at 3 millihertz you get a single cell, but if you use a slightly higher frequency, you get a double cell, just like what the earlier authors have published. So there is this points to a major problem, that the way you account for the systematics in your measurements is really affecting your inferences of the real circulation which you are after. So this problem is still not settled. So there is a currently ongoing effort, international collaboration, mostly with the Gong team and the Stanford team, which are trying to figure out how really to address this problem. Okay, so I will. This is a summary of my talk. The first part of my talk. I probably have another 5-10 minutes.
2 minutes.
Oh, okay. So let me quickly go through the other work which I have been doing recently, again with the collaboration with various teams. So before I explain all of that, let me first point out that the solar interior rotation, as I earlier said, that it is time dependent. So the rotation is not constant. If you most of the results here are attributed to very widely worked on by Anthea and his team. So what is shown here is that if you take you make the measurement of differential rotation on the sun, and you take an average over a solar cycle and you subtract from each monthly measurement, you see this pattern. What is shown here is the so-called torsional oscillation of the sun. The black dots are the sunspot locations as a function of latitude and time. What you see here is the red and pink color is the faster rotating band. There is a faster rotating band coinciding with the location where the sunspots appear. This is called the torsional oscillations. And this has been very well measured now. Oh, okay. So what Anthea and Basu 2 years ago or 2.5 years ago, what they found was that when they take the gradient of rotation, radial gradient of rotation in the near surface shear layer, very close to the surface. What they found was that this is actually again residuals in the gradient of rotation. What they found was that wherever sunspots appear near the surface at 0.99, it is blue, that means the negative gradient. So, the rotation gradient itself is negative, and if you see a residuals negative, that means it is a larger gradient here near the surface. At 0.99, wherever sunspots appear, the rotation gradient is larger, but if you go just slightly deeper at 0.95, that is at the base of the near surface shear layer, where there is a near surface shear, and you go to the bottom of that near surface shear layer, the sign changes, the rotation gradient sign changes. So, we have been trying to understand what really is causing this. Okay, so the questions one can ask here are, what are this changes in the rotation rate and their association with the sunspots? One can ask what causes these changes, how are these active region flows, which I earlier talked about in one of my first slides, how are the flows around active regions collectively together over, if you average over longitude, whether they can contribute to this rotation gradient which you measure. And those are the important questions. These are important questions because as you all know, the dynamo, the way dynamo works is that the sunspots come and appear and then they disperse, the flux is decaying, that forms a feedback to the operation of the dynamo. So, for the decay process at the surface, it is called the Babcock-Leighton process. For that, you need to worry about how these flows around active regions really disperse the flux. And on top of that, how are they related to the gradient of rotation, which I just showed you. Okay, so I will skip this. So, this is the result which we found, which is under review, which is close to being accepted. They are already reviewed, we are just working on the revisions. So, what is plotted here is the first top two panels show what I just explained, the gradient and change of the changes in the gradient of rotation as a function of depth at 0.99 and 0.95. What we did was we measured the meridional flow, as I told you, we have been measuring meridional flows. So, we did the residuals in meridional flows again in the same way as the residuals here in the rotation rate are calculated. So, what we found was that this here, this is the residuals in meridional flow. So, blue means equatorward and red is poleward. So, during the cycle period, when a lot of sunspots appear, when this rotation gradient is larger, which is blue, which is also coincides with the inflow towards active regions. The meridional flow is perturbed by the flows around active regions. So, if you take a residual meridional flow, you will find that this blue region will correspond to those locations, sorry. So, those locations where there is an inflow towards active regions. So, wherever sunspots appear, there is an inflow towards them, and that very well matches with the changing pattern of gradient of rotation. Okay. So, this is what we found, and so now the theory has to explain why there are a lot of active regions appear when there is a lot of flows driven towards the active regions, and why do they cause the change in the rotation gradient. Rotation is the east-west flow, whereas the meridional flow changes in north-south. A change in north-south flow causes this gradient in rotation change, change. So, in this particular way. So, our proposal here in our paper is that whenever there is flows across the latitudes on any atmosphere, you take even the earth, when there is a flow across latitudes, the major force which you experience is the flows experience is the Coriolis force. The Coriolis force turn the flows, if it is in the northern hemisphere, just like in the storms which we observe on the northern hemisphere on earth, they rotate anticlockwise. So, what that means is that when there is a flow across latitudes, it turns to its right. So, here when the meridional flow is perturbed due to active regions, there is a flow towards active regions in the northern hemisphere, it will turn to its right. So, this blue flow, which is coming from higher latitudes to lower latitudes, when it is acted on by the Coriolis force, it will try to oppose the rotation because it will turn to its right. So we believe that is why this rotation gradient is larger there. So this all right, okay. So just let me close with another result on this particular aspect. So here, what is plotted here is as a function of time again. The bottom three panels are the rotation gradient as a function of depth. You see this sign change. The larger gradient is blue, and it changes into a slower gradient at about 0.97 below the surface. 0.97 is about 20 megameters, 20,000 kilometers below the surface. So this particular sign change in the rotation gradient very well matches with the changes in the meridional flow, which we measure as a function of time and depth. All right. So we believe that we have found an explanation for why the rotation gradient changes that way, but it is yet to be published. All right. Okay. So this is explaining in terms of what really happens around active regions in the smaller scale. Okay, I will skip this, and this is again a cartoon picture, which what I was explaining before about how the flows towards active regions acted on by the Coriolis force, how they really behave. And this is a cartoon depiction of that. Okay, so this is my summary. So the near surface temporal variations correlate strongly with the active region magnetic fields. Inflows around active regions are a dominant source of variations. Coriolis force on these flows can explain the observed changes. And the meridional and zonal flows have correlated variations over solar cycle. And there are also north-south hemispheric differences which are there in our results. I didn't really explain that. And there are also cross-equator flows across the hemisphere. So all of them have large implications for the dynamo models. They are yet to be worked out. So I will stop here. Okay.
Thank you, Rajaguru, for your exciting talk about our viewers. Now the session is open for questions. Please raise your hand.
Thanks for the nice talk.
Yeah.
My question is, the magnetic field of the Sun is declining over the past few decades. Can you please comment on that?
Oh, the last few decades, you mean over several solar cycles it has been declining?
Constantly declining.
No, I think the current solar cycle is not really declining. It is actually larger than the previous cycle. Current solar cycle 25, is actually larger in number of sunspots are much larger than what we observed in the last cycle. So there was a trend in the previous 3 cycles, there was a declining trend, but it is now reversed. I mean, other experts here can, I don't really work on the amplitude of solar cycle as such, but I think it's not so. There is no gradual decline of the magnetic field over time. It's highly a stochastic process. We don't highly nonlinear process which is operating behind the operation of the solar dynamo. I don't think we really fully understand what actually determines the cycle to cycle variations. So there were a lot of proposals that it is declining, but it is not so. The current solar cycle is, Dibyendu is there, so he may answer you more on that.
Yeah, Dibyendu.
So I think we do actually completely understand why the solar cycle behaves the way it is in terms of the altitude variations. We now have models that can explain pretty much century scale solar cycle variations from one cycle to the other cycle. This is because of the stochasticity in the distribution of sunspot mechanics when they emerge. That creates different dipolar fields from one cycle to the other. And the dipolar field then feeds back to create the toroidal field which produces the sunspots. I think over the last 10 years we have a very good understanding of that. The models have progressed to be able to very clearly match the observations. Having said that, as Rajaguru said, there's still some uncertainties in understanding the solar dynamo mechanism. Not everything is well understood, but cycle to cycle variations more or less we are able to explain largely.
Are there more questions?
This is general curiosity. With all this kind of fluid complex fluid pattern, do you ever see shock fronts developing?
Not in the interior. I mean, so the solar atmosphere, of course, has lots of fast flows, shocks forming. For interior dynamics, is mostly small amplitude flows. Even rotation is very subsonic. So the sound speed near the surface is of the order of 10 to 15 kilometer per second. So we don't form shocks due to rotation. Yeah.
Any more questions? Okay, I have a very nice question.
Oh,
So you showed one of the images, the subtracted images.
yes.
IBIS. So are they band specific? Is it preferable to do any filters, two filters? Which are the bands specifically? One of the earliest slides.
This one or no?
Very beginning, one of the
Oh.
IB minus IR divided by those images.
Sorry, is it?
Yeah, somewhere there. Yeah, no, not here.
You mean the Doppler images?
Yeah.
Here?
This one, exactly.
So sorry, what's the question?
So this one IR minus IB, these are the.
Oh, so this is just that's the way Doppler measurement is done. In the intensity in the right wing minus the blue wing divided by the average.
Okay.
So that gives you the measure of the Doppler shift.
Okay.
Yeah. So that is. I just put this just to explain how exactly Doppler measurements are done, and yeah. So that's.
Okay. Thank you. Yeah. So let's thank Rajaguru for our next session.
I think it's still on.
So we have our next speaker is Manoj Purvankara. So he'll be talking about star and planet formation studies in the new millennium, key insights from infrared space missions.
What is that? Huh? Oh, there are two. Okay. Okay. So can you get the Google slide? Okay, get the Google slide and reload it. Just reload it once, yeah. And go full screen. Use? Which one should I use? Oh, so can you just do that laser pointer there?
Yeah.
Huh? No. Just go full screen. Go full screen. And bring your cursor here. Yeah, okay. Is it okay? Yeah. Yeah, can you hear me? Yeah. Good morning, everyone. Thanks to the SOC for inviting me and for this opportunity. Thanks to the LOC, Ananta, Abhay, Sushanta for all the arrangements. It has been fantastic so far. What I want to talk about today is about how 3 infrared space missions in the new millennium, in the last 25 years, have transformed our understanding of how stars and planetary systems form. As you can see from my title, that is the key message that I want to give you here. Needless to say, this is such a comprehensive review is beyond, you can't do it in 30 minutes. So what I will do is I'll be very selective, and in doing so, I'll also be a little biased towards the areas that my interests lie and where I have worked on. Just to provide you a larger context of for the galactic star and planet formation studies, see, 2 of the big questions in contemporary astrophysics is about how do galaxies form and evolve, and how do conditions for life emerge in the universe. And the process that is central to these 2 questions is what star and planet formation studies address, namely the question of how does interstellar matter end up as stars and planetary systems and eventually create conditions of life, and what are the physical processes that drive this transition. Now, it turns out that these physical processes that drive star and planet formation are best studied at smaller scales of few thousands. By smaller scale, I mean few thousands of AU to few hundreds of AU, and that is what I'm going to explain to you in this figure. This is a cartoon which tries to capture our current understanding of how star and planetary systems form, and basically the various evolutionary stages. So in the current paradigm, the star formation process begins with the gravitational collapse of a slowly rotating dense core, resulting in the formation of a central protostar, disk surrounding it, and an overlying envelope from which the material is falling onto the disk. So this is not an equilibrium structure, it's a free-falling envelope, it's a dynamically collapsing system. The disk forms because of angular momentum conservation. Material far away from the rotation axis of the system cannot directly collapse onto the star because specific angular momentum scales as r square, and then it has to lose some 12 orders of magnitude of angular momentum before it can collapse onto the central object. So instead it collapses and flattens and form a disk-like structure. Most of the material that goes on to build the star must be processed through the disk. At some time during this stage, bipolar outflows breaks out along jets breaks out along the polar axis of the system. The launching, acceleration and propagation of which is not entirely understood, and my talk mostly will be dealing with that in today's lecture. And eventually the envelope dissipates, and either by collapsing onto the disk or by the action of the outflow, and eventually you are left with a pre-main sequence star and a disk around it. These disks are the birthplace of planetary systems, and we call them protoplanetary disks. Eventually the disks also dissipate by forming planets and due to the effect of other dispersion mechanisms, and you have a main sequence star and a mature planetary system like our solar system. So this is these are the main evolutionary sequence that the way we understand star and planet formation. Now, so since I was talking about star and planet formation in the new millennium, so where were we at the turn of the century, at the turn of the new millennium? Of course, the modern star formation theory was already in place by the work of in the late 70s, and by mid 80s by work of Larson and Frank Shu and others, and by 80s the millimeter and submillimeter observations, single-ish observations, are already seen outflowing material from young stars, forming stars. And we had already known about the SCD classification system, that's famous class 0, class 1, flat spectrum. That by 90s they were in place, and even the protostellar phase itself was classified into various evolutionary schemes. And HST was launched by 1990, and HST by mid-90s, late 90s, HST had already imaged jets from young stars, newly formed stars. And HST images of debris disks also laid to rest any speculation about whether disks exist or not. So by the turn of the century or the new millennium, we knew so young stars have disks and they drive jets, and there are outflows, etc. And why do we need, so these three space missions that I am talking about are mid-infrared and far-infrared missions. So why do we need mid-infrared and far-infrared to study star formation? See, young stars are deeply embedded. For example, protostars, the line of sight extinction AV in V magnitude can be several hundred magnitudes, and they are not even visible in the near infrared. So they're deeply embedded. So you need, so because of the heavy extinction, you need to go to longer wavelengths, mid-infrared and far-infrared wavelengths. The other reason is for the youngest protostars, the SED, the spectral energy distribution, peaks at around 100 microns. So to characterize the protostellar properties, you need to sample the peak of the SED very well. And that is what Herschel did, one of the space telescopes that I'm going to talk about. But more importantly, it's a spectroscopy, mid-infrared and far-infrared wavelength ranges. There are several lines which have powerful diagnostic potentials, such as so what I've shown here is an JWST spectra, NIRSPEC and MIRI spectra from 2 micron to 28 micron. The broad features that you see are ice absorption features, water ice, CO2 ice, CO ice. These are the silicate absorption feature. So since we are observing the protostar, the light from the protostar passes through the protostellar envelope before it reaches us, and it absorbs, the dust in the envelope absorbs in the silicate and forms the silicate absorption band. And then at 15 micron there is another CO2 ice band. But in addition to the ice bands, you see various emission lines. So you have fine structure lines, iron 2, neon 2, etc. in mid-infrared spectra. But also you have molecular lines, such as molecular hydrogen lines. These are the pure rotational transitions of molecular hydrogen lines. We have something like S1 to S14, S15 or so in the MIRI and NIRSPEC wavelength range. And you see all of them here. In addition, you see a bunch of lines here in so this is a water ice feature, and this is the methanol ice. You see, these are water lines. These are row vibrational lines of water from vibrational state 1 to 0. And then this bunch of lines that you see here are the R and P branch of the carbon monoxide row vibrational, the fundamental 1 to 0 transition. So it's extremely rich in spectra. And then if you go to far-infrared wavelength, this is a Herschel packed spectra of a protostar. Of course, you see one of the major coolant, the O1 63 micron line, and C2, the other fine structure line. All the other lines you see here are due to carbon monoxide, pure rotational transitions of carbon monoxide from 14 to 13 to up to 45 to 44, almost 30 lines. And there are some water lines as well here. So this is the primary motivation of going to mid-infrared. So the rotation, row vibrational transitions and pure rotational transitions of several species fall here, and also the fine structure lines. So the three space missions that I'm talking about are Spitzer, Herschel, and JWST. Spitzer was launched in 2003 August. It's in an Earth trailing orbit. It has a primary mirror of about 0.85 centimeter. It had 3 instruments on board. IRAC and MIPS were images, but the spectrograph was IRS, the infrared spectrograph, which had the wavelength coverage from 5 to 40 micron. In contrast, Herschel was the largest infrared telescope ever launched until JWST was launched in 21, 3.5 meter primary mirror. It's an L2, and it had 3 instruments, and I'll primarily be talking about the PAX instrument, which had both imaging and spectroscopic capability. But Herschel operated primarily in the far infrared wavelength from 50 micron to up to 600 microns or so. Then JWST, which was launched in December 2021, 6.5 meter mirror L2, and the wavelength range, of course, goes from 0.6 to 28. It had several instruments, and I'll primarily be talking about NIRSPEC and MIRI, and these are spectral images. These are IFUs, integral field units. So you get spectra of an entire image space. So both NIRSPEC and MIRI, and the wavelength coverage is from 0.6 micron to 28 microns. I was lucky enough to be involved in all 3 space missions. During my early postdoc days, I was part of the Spitzer IRS instrument team at University of Rochester, then part of the couple of Herschel Open Key Time program, primarily with the HOPS program, which had 200 hours to survey Orion. And then with JWST, I'm part of 2 GEO program, and particularly this one, the Cycle 3 GEO program. We got 192 hours on JWST, and this is one of the largest galactic science programs with JWST. So what are the major advances in the new millennium? So I'll be very restrictive. I'll primarily try to focus on mass accretion and ejection in protostars and protoplanetary disks, because time doesn't allow me to go into other areas. So I'll mostly be talking about the protostellar phase and the protoplanetary disk phase. So let's look at the new insight. So what did Spitzer see? So this is the mid-infrared spectra of protostar from Spitzer. Spitzer had both low resolution and high resolution mode. By low resolution I mean resolving power of 60 to 120. You could only see broad ice features and silicate absorption here. You couldn't see emission lines here. But when you go to higher resolution, this is a spectra of NGC 1333 IRAS-4b. You see the sulfur 1 and silicon 2 fine structure lines, and the OH doublets that I have marked in pink. All the other lines that you see there are pure rotational transitions of water in the ground vibrational state. So it's extremely rich spectrum. So one of the major results that have come out of Spitzer was on protostellar mass accretion ejection relation in protostars. Now, for more evolved objects like class 2 or protoplanetary disk, which was optically visible or visible in the near infrared, this was done in the 90s also using large telescopes and also HST. And people had established some sort of relation between m dot out and m dot accretion. See, that ratio is important because most of the jet launching mechanisms predicted direct proportionality between mass loss rate and mass accretion rate. And that proportionality constant actually tells you something about the magnetic lever arm from which the jet is launched. So that's that essentially fixes the footprint of the magnetic fields which are launching this disk, and it was thought to be discriminatory between these models. But what this particular work did was a large sample of protostars. See, before Spitzer we couldn't do this. Although ISO was there in the 90s, it didn't have the kind of sensitivity that Spitzer had. This particular work which I was part of, we observed 100 protostars. We obtained the high resolution Spitzer spectra of 100 protostars within 400 parsecs from us in the star forming regions. And we measured the mass loss rate from the fine structure lines of iron and silicon 2 from shock modeling, and then measured the accretion rate, and then this plot shows you the mass loss rate is on the y-axis and the accretion rate on the x-axis. So this for protostars class 0 and class 4 and flat spectrum, it follows the same trend as the class 2 more evolved objects. That was the main message here. And even with including protostars, we couldn't really use B, the proportionality constant or the magnetic lever arm. The inverse of that is related to the magnetic lever arm. We couldn't really discriminate between these three models. The models that we are talking about are disk wind model, the X wind model, and the stellar powered accretion model. At least those were the models discussed in the context of protostars. Moving on, so with Herschel, I told you about the CO line. So we were able to demonstrate, we were one of the first group to demonstrate that carbon monoxide is the major coolant of the shock gas in far infrared. And contrary to what was thought then, everybody thought it was water. And we used the carbon monoxide line luminosity as a proxy for mechanical luminosity, and we found a good correlation between the carbon monoxide far infrared line luminosity, which is the energy dissipated by the shocks. It's in some way measure of mechanical luminosity of the flow, and ELBOL, the protostellar luminosity. There's over 3 orders of magnitude, but we could not find a relation, we could not find a correlation between age, and this is consistent with episodic accretion driving these flows or episodic mass loss rates. But together with some other results from submillimeter outflows, we were able to argue that although there is episodic accretion, there is also an average mean drop in the accretion or mass loss rate. Moving on, let's look at what we have learned from JWST. So these are the two main conclusions that we so far have been able to make from JWST. So we see jets and winds. We see collimated a high velocity jet. We see a wide angle slow moving jet. So, or in other words, we see this nested structure or stratified flows in morphology, in kinematics, and in excitation. And I'll demonstrate this in the following slides. And the most important takeaway message is we clear detection of wide angle winds driven from the disk. See, until now for protostars it was thought that this collimated jet with lateral momentum transfer is entraining the gas in the envelope, and that is what we see as wide angle flow, not only in infrared but also in sub-millimeter, millimeter wavelength, the famous CO flows. But what we are seeing here with JWST is that it's much narrower than the cavity walls, and it's actually the material being lifted from the disk, and that is what I'm going to talk about. And the evidence that I'm going to show you is mostly based on this particular geo program that we are part of. My students are leading this analysis. You must be familiar with this jet. This is the NIRCam image. This image is 2 arc-minute across. This is HS211, and the MIRI and NIRSPEC IFUs that we are talking about is only the innermost part of this, a few thousands of AU. So this is much larger than that. So this 2 arc-minute across, and the MIRI IFU, MIRI and NIRSPEC IFU are 6 to 8 arc-second across. So all the images, spectral images that I'm going to show you are the innermost part of the protostar. So with this program, IPA program, we looked at 5 protostars spanning in luminosity from 0.1/10th of a solar luminosity to 10 to the 4th solar luminosity, and in masses they range from 0.1 to 12 or so. So the nested structure in morphology. What I'm showing you here is that this is a continuum image at 4 microns or so, and at 4 micron the scattered light dominates, and this shape you see is because the light scattered of the envelope cavity walls. So that kind of traces the width of the cavity. This is the molecular hydrogen line, the S9 line, S11 to J11 to 9 transition. You see it's much narrower than the cavity itself, and then in the ionic lines, in the fine structure line, we see a highly collimated jet. So this is the nested structure in morphology that I'm talking about, and we see this similar structure in all the other protostars. So B335, another one of the low luminosity protostar. So this is the continuum at 4 micron. You see the cavity clearly delineated in scattered light, and then this is the hydrogen line, S11 line. This is much narrower than the cavity. So this is not material in the cavity wall being entrained. This is actually the material being driven probably from the disk. And of course in the iron 2 you see much more collimated structure. Same for slightly more luminous protostar, HOPS 370. This is the continuum at 4 micron, S11 line, and the iron 2 jet, much more collimated. So that's about the nested structure in morphology. How about, so let's quantify that. What's the opening angle? Opening angle is the half angle. So if this is your flow, the half angle of that, and so here you measure the width of the jet and then plot it as a function of distance from the source, and you measure the opening angle about 2.6 degree or so. So for the highly collimated jet, the opening angle is always less than 5 degree, and we see this in other sources too. We measure the opening angle. For collimated jet, it's less than 5 degrees, so it's very collimated and it's very compact. The inner jet, collimated jets have high velocity. After correcting for inclination, for the lowest luminosity source, IRAS 16253, we have a velocity of about 170 km per second. See, the sound speed in these systems are few kilometers per second. So, and for other sources also, we see the collimated iron 2 jet far exceeds 150 km per second or so. And then look at the molecular hydrogen winds. We also see that when you go from lower excitation hydrogen line to higher excitation hydrogen line, the opening angle narrows. I mean, the opening angle becomes smaller. So this is the S1 line, the lowest excitation hydrogen line, and this is S5 line. So you can already see it's narrowing, and then S11 it's really narrow, and we actually measured the opening angles of this, and we really see that trend. So higher excitation lines have smaller opening angle or narrower. We see the same trend in other sources too. So this is the lowest excitation hydrogen, the S1 line, then this S5 line, and S11 line. So progressively it gets narrower. Same for HOPS 370. And we also see this higher excitation lines are also warmer. So we've constructed what is known as the rotational diagram. This is just Boltzmann diagram. You plot, the number density, the level population ratio against the energy level. Then if it is in LTE, you get a straight line, but clearly this is not in LTE. We need two components to fit it. The low excitation hydrogen, molecular hydrogen lines are at a lower temperature in the range of 600 to 1000 Kelvin, whereas the higher excitation hydrogen lines are at 2000 K. So the higher excitation lines are narrower, the wind geometry is narrower, but also warmer. The gas is also warmer. And same we see in the other two sources. And interestingly, so remember the collimated jet was moving at 150 km per second or so. The wide angle hydrogen winds are moving at 20 to 50 km per second. These are the position velocity diagrams. Velocity is in this y-axis, and that's the positional offset. So it's typically around, if you correct for inclination, it typically comes about 20 to 50 km per second. So wide angle winds are also slow moving. So that's the nested structure I'm talking about. Smaller opening angle, more collimated, they are higher excitation and moving faster. The larger opening angle, wider winds, they are lower excitation, lower temperature, moving slower. But what was really surprising was the momentum rate in the molecular hydrogen winds far exceeded those in the collimated winds, even though the velocities were much higher for the collimated thing. So on the panel on the left, I plot m dot out, that is the outflow rate, and that of course is much higher. The orange point is for molecular hydrogen lines and the blue points is for iron 2 lines or the collimated jet. So you see, this is not surprising. Molecular winds carry more mass, but what is really surprising is the momentum rate or the outflow force. It's order of magnitude larger in hydrogen lines in these two sources. For B335, it's comparable. See, B335 is peculiar. It has recently undergone an outburst in the last 1 year or so. So that we still need to understand. But this difference is sort of an order of magnitude or larger. See, the earlier people thought this collimated jet, that the jets are launched and then by lateral momentum transfer it kind of entrains the molecular material, and that is what we see as the wide angle flow. But what we are finding is the momentum rate in the wide angle flow far exceeds by an order of magnitude or so than the collimated. So collimated jet can't be driving the wide angle flow. And moving on to protoplanetary, this more evolved, slightly more evolved systems, we see the same thing. So you see in the iron 2 line, you see highly collimated jet, and then in hydrogen you see this wide angle structure, and that's just the continuum for your reference at 14 micron continuum. This is HS30, again iron 2 highly collimated jet, and the molecular hydrogen flow is wide angle. And here you also see when you go to higher and higher excitation lines, it becomes narrower, progressively narrower. This is the S1 line, the lowest excitation hydrogen line. It looks as if it is almost tracing the disk. This is almost an edge-on disk. And then when you go to higher and higher, you see it's becoming narrower, the opening angle. And we also see this is for more evolved systems. So there is no envelope here. So the behavior is exactly the same. And then this leads us to believe that it's disk probably which is doing all this. And so it's regardless of whether it's a protostar or a simple protoplanetary disk, the underlying mechanism probably is the same. So here also we see higher excitation, the winds seen in higher excitation H2 lines are warmer, about 1000 K or 1500 K. We just put this 1 point for the protoplanetary disk here along with the protostellar thing. We haven't worked out the iron to the collimated jet mass loss rate. We are still working on it. But if you just look at the molecular hydrogen mass loss rate or momentum rate, they are similar for the similar mass thing. The oranges, it's not very different from that of protostar. So all these independent evidence seem to suggest that we are looking at the similar underlying mechanism. And just to show you the Jessy, how? 5 more, okay. Yeah. So just to show you a comparison of the disk spectra between Spitzer, what we saw in Spitzer IRS and JWST MIRI, this was a Spitzer spectrum. You hardly could see any line. This is the JWST spectrum of the same object. These little blips that you see, these are not artifacts or noise. These are real lines. It's so rich that it's, every group is struggling to figure out how to go about with the analysis. So this is another example. Extremely rich in lines, the protoplanetary disk. So, here is another example. So among those rich forest of lines are also hydrogen lines, the higher order hydrogen lines in mid-infrared. These are the Fun series and the Humphrey series. And the hydrogen lines are often used as an accretion indicator, accretion proxy in young stellar objects. But the problem with the shorter wavelength lines, whether it's H alpha or H beta or the near infrared lines such as bracket gamma or passion beta, is that there are opacity effects, and extinction is one thing, and then there are opacity effects. Then it's also that the jets also emit H alpha and bracket gamma and passion beta, whereas the mid-infrared lines, the higher hydrogen lines, the Fun series and Humphrey series and higher, the contribution from jets are minimal. So they are purely, they mostly trace accretion. So my postdoc Sridharan gave a talk on the first day about this. So we identified several hydrogen lines, and we derived an empirical relation between the line luminosities and the accretion luminosity, and this can be used now by other groups. So what it, among other things, what it really provides is an opportunity to simultaneously measure mass loss rate and accretion rate. So in the same spectra, MIRI spectra, you have this hydrogen line and you have the mass loss indicators like iron 2 or H2 that I just showed you about. So just to summarize, in IR space missions, the last 25 years have significantly advanced our understanding of mass accretion ejection in young stars. It has also contributed significantly in other areas, but in 30 minutes I could only focus on this. And the main take-home point is the recent results from JWST suggest a paradigm change in our understanding of jet launching, in the sense that instead of accretion driving winds, it's the winds which are making accretion possible. So jets and winds are not a consequence of accretion. It's jets and winds that make accretion possible and to build stars. Just to advertise the latest program, FA, this is a 192 hours program on. So we are obtaining NIRCam images of the Orion integral shaped filament, this entire filament, and also the spectral images in NIRSPEC and MIRI of 13 protostars. So we already got a first set of data. This is HOPS 88. So we are already in for a surprise. See, you see red shifted and blue shifted outflow. This is almost on the plane of sky. In molecular hydrogen S5 line, you see the wide angle component. Look at the blue shifted part. You see the wide angle component which moving slow around 10 km per second, but it also has a collimated component. So moving at a velocity of 30 km per second or so. So it's all over the place. So it's very fascinating, and all this work is made possible by this my group, the students and postdocs in my group in TIFR. Sridharan, Bihan, Himanshu, Vinod and Sujay, they are the current members, and Mayank has just moved out, and other postdocs who are part of this. I'll stop here and put the summary slide and take questions.
Thank you, Manoj, now the session is open for people.
Manoj, very nice talk. I would like to understand, because when you are talking about higher momentum rate as you go away, you essentially are talking about higher mass loading in the outer part of the accretion disk. Because when you have mass loading in the outer part of the accretion disk, your wind becomes much more heavier, and therefore you have higher momentum rate.
But it's
That can you from your observations make a radial dependence of the magnetic lever arm?
Yeah.
That would be an interesting thing, like an outflow and inflow rate at different radial points from the inner part to the outer part. Can you do that?
Yeah, so we are still working through the data. No, that's a good point. But I just want to point out that it's not a given that when you go to outer disk, you will have to load more mass. See, when you have a larger magnetic lever arm, with very little mass, you can extract as much angular momentum. See, when you are closer to this, you need to load, you need the mass, it's much more mass than to extract or take away the same angular momentum as here. So it's not a given. So what we are done here is a slightly simple analysis. We added all the hydrogen mass in the flow, and then even though they are moving slow, that works out to be much higher on it, momentum rate. Whereas the collimated jet, which is moving very fast but very little, so it's very little. We tried various different models. It's very little mass in the collimated mate. So it's not very clear. So yeah, so ideally that is what we want, a radial run of, with the radius of, how these various parameters change. Yeah, we'll work on that. That's just beginning.
Hi, Manoj. So, H1 as a efficient trace seems quite good. But my question is, I'm curious to know the special location of the H1 emission, whether it's coming very.
No, it's not. There is no extended component. We have spatial resolution JWST. It's from the compact source, central source. No extension. Whereas you see other fine structure.
No, I'm not. I'm talking about extinction. What I'm asking with JWST, IFU, can you say what is the special?
Yes, that's what I'm not talking about extinction. I'm talking about extension. It's compact. You can't resolve it. It's in the central source. We don't see it anywhere else. So with JWST, the best resolution we get with NIRSPEC spatial resolution is 0.1 arc seconds. So within that resolution, we don't see any extended component in the mid-infrared H1 lines.
So you assume that it is maybe within few AU? That's coming?
We can only 0.1. So for the closest source that you observed, it's 0.1 is about 30 AU. So we can only say that now. So we can, yeah. So it's coming within, there is no extended component. Whereas in bracket alpha, we see jets contributing significantly. In fact, dominating bracket alpha emission. Whereas higher Humphreys and Fun series, they're coming only from the central source. So given our spatial resolution, it's not extended.
Anyone else after that? Nice result. Of course, my question was very similar to what we had, but particularly the H211, which is the closest one, how close you have been able to go to the source?
Yeah, so Sarida, given the spatial resolution, for the closest that we observed at 120 parsec, it's 30 AU.
Which I think even from a sub-millimeter they have been able to go.
Yeah, see, ALMA can perform much better in terms of spatial and spectral resolution, that's true. But that is longer wavelength lines, yeah.
I also wanted to comment on the fact about that onion line structure, because I think earlier also people had made measurements with VLT and so on and had found that this kind of
Yeah,
structure
yeah, yeah,
to be much better.
yeah. Also HST, yeah. So that was there, yeah. But mainly fine structure lines. Even they were talking mostly about fine structure lines. Even the onion structure, the velocity, opening angle thing. But here we also have the H2 lines. So the pure hydrogen lines, rotational lines, it's come only in the mid-infrared. So that's the advantage. Yeah. For a few sources it was done with VLT and HST. Yeah, that's true. In the 90s, early 2000s. Yeah. We have a mass loss rate, which I showed in that plot. Let me, here. Yeah, so M out is very small. 10 to the minus 7, minus 6 solar mass per year. So is that, yeah, that's the mass loss rate between 10 to the minus 8 and 10 to the minus 6 solar mass per year. These are preliminary estimates, which might get refined in the days to come. Yeah, that's a very small fraction of the.
We have time for one or two more questions. I have a question. The collimated jet versus the wide angle and the low excitation versus high. What is the temperature range you observe there? Is there a measurement?
So for H2, yes, that is what I was showing you, that rotational diagram, no? yeah, I didn't explain it well. So let's look at this. These are these are the hydrogen. This is S1 line to up to S13 or so. So we are not able to. So you can clearly see. Just look at the blue lines. You can clearly see you can't fit it with a straight line. So there has to be at least 2 component fit when we do. For the low excitation lines, the temperature that we derive. So we fit it with the it's a 7 parameter fit. We simultaneously fit extinction also. So for one component, it's a 3 parameter fit. That rotational temperature. See, Jessy, these are not physical temperatures. These are excitation temperatures. Unless if it is an LTE, that's a physical temperature. We don't know. But hydrogen, typically people think it's an LTE. So this would be closer to the physical temperature. But strictly speaking, this is the T in the Boltzmann equation, which is an excitation temperature. And since we are dealing with rotational rotational levels here, we call it rotational temperature. The rotational temperature, it's for the low excitation component is it ranges for different sources between 600 to 1000 Kelvin, whereas for the high excitation hydrogen lines, the rotational temperature ranges from 1500 to 2500. So it's warmer. That is what I'm saying. The high excitation, narrower thing seems to be warmer gas. Yeah, so we don't understand exactly whether this is the same mechanism which is producing both or so we haven't really figured that out yet. This is what we see. We see the collimated jet in fine structure lines. See, what we really see is only the shock gas, even in the collimated thing. The most of the gas probably we don't see. Only when it gets shocked and ionizes things, and so we are only seeing the shock gas. Then we have to use models to get to the total density and all that. And hydrogen, hydrogen doesn't have a permanent dipole moment. The moment you see hydrogen quadrupolars transition, it has to be shocked. Otherwise, you have to have plenty of UV to excite it. So these are shock excited lines. But how exactly, what exactly is the mechanism? So we are just learning about it. It looks as if the wide angle winds have a different origin. So it's still we are trying to figure out. See, the JWC data has started coming in the last 1 year. So yeah, still we are figuring out. We can talk about it if you want. I can give you the nuances.
Yeah. Let's thank Manoj and Yogesh.
So yeah, Yogesh, you should get this help. This you have to wait. There are 2. Though you need 2 speakers.
The title of the talk is Exploring Open Clusters to Unravel Galactic Structure.
One for the broadcast and one for the ring. Yeah, please. 25 minutes. Yeah. पॉइंट है वहाँ पे, so वहाँ पे वो डिजिटल पॉइंट है. चलो ठीक है. I'll just put it in. As you wish. It is working. This is to context previous, and this is the pointer, digital pointer. Okay, fine. Okay, thank you very much, and welcome to all of you, and thank you to SOC for giving me opportunity to give a talk here, and thank you to all of you for giving me opportunity to work in the ASI Executive Council also. So for your voting, thank you to all of you. Yeah, so I am focusing my work on the open star cluster and understanding of open star cluster in context of galactic structure. So there are a couple of people who worked in this study. Andre from the Russian Institute, Jan Moria, I'm my PhD student, and Sagar Malhotra, my master thesis student. So they worked in this work. So to brief you about the open star cluster, as you have already heard about from the Manoj or the star forming regions, and this is the successor of the star forming region. So when you have the star forming region and over a period of time you see such kind of bright stars, that is called open star cluster. So these are formed from the one molecular cloud, and because they are formed from the one molecular cloud, they are almost at the same distance and at same age. And in fact, because it is formed from same molecular cloud, they have the same chemical composition. So all these stars which you can see here, okay, point is not working. Okay. No, point is not working. No, this is working, but not the pointer. So anyway, okay, this is tough one. Okay, fine. So centrally, you can see there are many stars altogether. They are gravitationally bound stars, because they are formed from the same molecular cloud, so they are gravitationally bound. They are one entity actually, and all the stars. So they have same distance, chemical composition gauge. Only difference is that they are different masses. So in a star cluster, you can have range of masses. Of course, there are less number of stars having higher masses and more number of stars having the lower masses. So that is the mass distribution, and this mass distribution actually help us to understand the star cluster and star formation. So as you see the left side of the HR diagram, these stars having their different masses fall in the different segments of the main sequence of the HR diagram. And as you see here, from the same star cluster and having the star of different masses, they have different spectral class, different mass, and they fall in different regions. So you see a stretch of the stars in the HR diagram, and through which you can actually characterize the cluster, you can determine the parameters, and then that's what we did with this HR diagram of the star cluster. As you can see here, there are various star cluster nodes. Of course, this sample of we have a lot of other star clusters also, but this is just to show that there are various star clusters, and this point is called turn off. So this depends upon the age of the star cluster. So how old the star is? If the star is young, so there will be no turn off, and as it becomes older and older, you will have that turn off line going down across the HR diagram, and from that turn off point you can determine the age of the cluster also. So you can have the information of the age from this diagram, as well as from the left this color index B minus V, you can have the temperature information, and from the absolute magnitude you can have the distance information. So we observed star cluster. Earlier we used to observe all these star cluster from the ground based telescopes. Nainital, where I work, have a lot of telescope. So we started from 1 meter telescope, and now we have 1.3 meter telescope and 3.6 meter telescope. So we have a legacy of working on the star cluster since 1972. So we used to observe the star cluster. Beauty of the star cluster is you don't need to have a very large telescope. I mean, you can have a small telescope and you can monitor these stars. Only thing is that if you have a small telescope, you will see only the bright star of the star cluster, and as you have the beta and bigger telescopes, you will go fainter down and means lower mass. So but you can do this kind of work even any telescope. So we have observed star cluster from an entire telescope, and a lot of cluster in the last 30-40 years in fact, and we have determined star cluster. So earlier, yeah, so how to see the dimension of the star cluster. Earlier, when we had just only the photometric observation of the star cluster, we used to see the image, and assuming that this is a spherical distribution of the star, we used to check the this concentric region in the star cluster, and determine the mass stellar density and plot them with the radius, and where this density matches with the your field region density, then we assume that that is the extent of the star, assuming that the whole star cluster is spherical, which is not the case now. So, and then we observe this cluster because we need to infer the information, the temperature. So we need multi-band observation. So we used to observe in different bands. Here I have shown B minus V, but we can observe in UVB, RI, even you can go to even the infrared. So observe at least in 2 clusters, get this color information, and then from the color information you can actually color diagram, you can determine the reddening or extension in the direction of cluster, and then from the color magnitude diagram you can determine the this temperature information or extension information. Here you can determine the distance modulus information, and from the turn-off you can determine each. So you have all these called isochrone fitting. So you have the theoretical HR diagrams, and you overplot your theoretical HR diagram on this star cluster, and you get the information. So you determine various parameters from this observation. So, but this change with the with the space mission Gaia, and Gaia has revolutionized this field in a significant way, because earlier we used to observe the star cluster one by one in different filters. So it took time to observe. So from the ground-based observation we have only few thousand clusters, I mean less than 3,000, and now the Gaia has changed scenario, because Gaia is observing whole sky, and 2 billion stars are reported. And importantly, they are giving you the multiple band observation, so multiple filter observation, and the radial velocity observation, proper motion detail, parallax information, because as I said, the star clusters are bound entity, they are formed from the same molecular cloud, and they move in a as a single entity, so their proper motion is same, their parallax is same. So Gaia is giving all this information. So we use this Gaia data now. Instead of having the ground-based observation of cluster one by one, you have the volume of data, 2 billion stars, and determine the various parameters. So as you see here, this is from Gaia. So in Gaia, so here in Gaia, so this is proper motion detail from the Gaia, and you can see the motion of the star if it is in the same direction of, because these are part of the same cluster. So you, from the motion itself, you can tell that okay, this is the same star combination, same star from the cluster. And then here in proper motion plane also, you can see the all star are following the small circle because they have the same proper motion. So then you have the spatial variation, RA and DEC. Of course, as I said earlier, we used to assume that star clusters are a spherical entity, but that is not the case, as you can see here from the RA DEC distribution. So it is very centralized, very dense in the central region, and then very sparse in the peripheral region. So this is a typical star cluster observed from the star cluster Gaia. And then you can always do the color magnitude diagram to determine all these parameters. So Gaia offers this 5D characterization of star, which is ideal to identify cluster members. You don't need to observe cluster one by one, and you just take the data and Now people have used this machine learning to identify the star cluster. So there are volumes of star cluster are known. I mean, people are discovering star cluster in hundreds and thousands. So in this process also, what happened that there were some known star cluster, and because the Gaia proper motion and parallax information is there, so what we have noticed that there are some known star cluster which were identified as a star cluster, but now from the proper motion, they are not the star cluster. As you can see, this plane star are moving in random direction. So they were assigned as star cluster, but they are not the star cluster anymore. From the guide data, we infer this information. And in the left side, there is a star cluster. As you see, most of the stars are going in the same direction. So these are the stars which are part of the star cluster, but in the right side, it is not. So we identify star cluster, but at the same time, using this guide data, we have discarded many star clusters which were known as a star cluster earlier. So there are few examples here. As you see here, these were identified and well-known cluster, because when it is given in the NGC catalog, so it means that these are known for a long time, but these are no more star cluster. And in fact, more than 1,000 star cluster, open star cluster are discarded from the guide data. So these are not in the list anymore. So what we did now with the guide data, so we observe star cluster and then check their proper motion, and in proper motion plane where this proper motion in r direction and that direction, you check the proper motion, and you have the parallax information, and then you have the color magnitude diagram. So you have a clean diagram where you can really identify. Earlier we used to give a probability to a star member, whether it is a 50% probability of having a cluster member or 70% having a cluster member. So, and the different authors used to have a different criteria. But now you have the star cluster where they fall in the parallax diagram, parallax plane, and then they are in the proper motion. And you can see their HR diagram here, and it is very clean diagram, and one can determine parameters quite nicely, very precisely. So as you see in this list, there are so many star clusters are reported by different groups. Basically, most of them are machine learning. So where even thousands or even 628, that kind of number are reported. Of course, where you see the 2017 or 1910, they have used the previous reporting also. So there are hundreds and thousands of star clusters are reported by various groups. So recently what we did, we have combined all these catalogs together and cross-identify them and found that, okay, there are more than 6,000 star clusters are known. So as you see in this diagram, we have plot, this is the Gaia diagram of Milky Way galaxy, and these are the star cluster, all the yellow dots are the star cluster. And from this diagram itself, you can see that these are nicely overplotted in the galactic disk. Most of the star cluster, in fact, are in the galactic disk. So what we did now, as I said, we have more than 6,000 star cluster now. We can utilize this sample, this large sample of star cluster, to understand the galactic structure, primarily the galactic disk, because as you see this star cluster, they are nicely following the galactic disk, and they have different age. In any other stellar population, if you see, whether you take this molecular cloud, star forming regions, OB star, Cepheid, or Lyrae, so they have a certain age range. Here in case of one star cluster, you have a range from few million year to almost 10 billion year. Similarly, the distance scale, they are very close by, very many star clusters in our solar neighborhood, and they are detected up to more than 10 kiloparsec distance. So you have a whole range in the distance, whole range in age. You can use this star cluster to study the dynamical evolution of the galactic disk, and the spiral arms, because we know that these star clusters are tracer of the spiral arms. They are formed in the spiral arms. So we have the many young star cluster. We can use this young star cluster to trace the spiral arms using the open star cluster, and how the spiral arms evolves over the time. And then some of the star cluster, the metallicity is also reported, and of course not all of them. So we can use this these star cluster to understand the chemical evolution of the galactic disk. So these are a couple of programs which we can take up with this bunch of star cluster. And this is the typical spatial distribution of the star cluster of different ages. As you see, the top one less than 200 million year, 200 to 500, 500, 1000. So of course, these star clusters are still confined in solar neighborhood. The annular region given is 1 kpc, 1.75 kpc, and 2.5 kpc. So still, most of the star clusters are still, we can say in solar neighborhood, not very far off. Of course, there are few which lie even beyond the 10 kpc distance, but most of the star clusters are still confined very close to the galactic plane. And importantly, if you see the global cluster open star cluster having more than 1 billion year, the fourth plot, you will see that there is lack of old open cluster. So we try to understand in our sample that whether really there is a significant drop of the open star cluster when they are older. So we have noticed that only 2% of total older cluster are found in the solar neighborhood. So almost within this 700 parsec of the solar distance, only 2% of the total old star cluster. When I say old cluster, it is greater than 700 million year old. So only 2% fall in the solar neighborhood, very close to the sun. And in that region, within 700 parsec, only 7% of the total cluster are the globular cluster. Old open clusters. So we have a lacking of old open cluster in the solar neighborhood, and there are a couple of regions are proposed. Like here we have the more frequent interaction with the molecular cloud. So when you have more frequent interaction with the molecular cloud, or even tidal disruption, so the cluster disrupts over a period of time. And other thing is that we have the mass segregation effect, where the massive stars comes toward the center of the cluster, and then these less massive star or fainter star go towards the peripheral region of the cluster, and over a period of time, these massive stars are totally evolved because their lifetime is small, while these small massive cluster, they evaporate from cluster, they leave the tidal radius of the cluster. So finally the cluster disrupt or dissolve. So we will not see the cluster. So over a period of time, due to all these regions, tidal stripping or spiral arm shocks also, so we will lose old star cluster. So Lammers et al. Given a rough estimate that what is the typical mass which where the cluster survives up to 1 giga year. So we have calculated that to survive a cluster for even more than 700 million year age, you need a star cluster having a more than 4,000 solar mass cluster. So if it is richer than this 4,000 solar mass, it may last longer than 700 million year. If it is not, because most of the cluster are not that much massive, so they will not survive, they will not reach to this old stage. So of course, other people have also started working on the data, because there are a lot of star clusters reported. So Kenton Godin, one of them, have also discovered a lot of star clusters using the Gaia data, and they have plotted this diagram of the star cluster in the RGC and the distance of the galactic plane, distance of the cluster from the galactic plane, that is called Z, which is basically d sine b. B is the latitude. So they have plotted this star cluster, and see, this is the inner region. When we say the inner region, it is the distance toward the galactic center from the sun, and we assume that it is like 8.15 kpc from the sun. We are sitting here, sun distance is 8.15. So when we say this is inner region, so this is the region which is towards the galactic center, and this is the outer region which is away from the galactic center, anti-centered action. So most of the star cluster are confined very close to the galactic plane in the inner region, while in the outer region they are scattered, they are off from the galactic disk. So you can see here, we will further discuss about this in next few slides. So this is clear picture that over a period of time, they leave the this galactic disk. So I also draw this diagram, because if I go back here, in this picture, they have also shown the cluster with the age, with the various colors. So to clarify it more, I have drawn this number of star cluster within log h jet plane, where the distance of the star cluster from the galactic planes is given in a function of the log their age. And you can see here again, these young star clusters are lying very close to the galactic plane, galactic disk, and as they evolve, they leave the galactic disk. So combining both of them, that towards the galactic center, you have the star cluster, and they are young, which are very close to the galactic disk, and to outside in the anti-center direction, or away in the outer region, these star cluster are scattered. They are going off from the galactic disk, so they are going away. So one of the reason for this is that when you this star cluster and the galactic disk, very close to the galactic disk, the gravitational potential is strong, and they are there, but outside in the outer region of the galactic disk, this gravitational potential is less, and so if you have less potential, there is a chance that they may leave the galactic disk. And for the older cluster, the destruction time is also they will important, because they will not survive if they are in the inner region and very close to the galactic disk. This cluster will not survive because the tidal interaction, because of the encounter with the molecular cloud and all these things. So you will not find many older cluster in the inner galactic disk, so which we have seen. One of the thing in this diagram, we have noticed that if this is the galactic plane, mid-galactic plane z equal to 0, which basically is b equal to 0, so only 40% cluster are above this plane and 60% are below this plane. So most of the cluster are in the southern hemisphere in comparison of the cluster in the northern hemisphere. So there is a reason for this, and we will further discuss about this. But before that, I will highlight the distribution of the star cluster in the xy plane, where these L and B are converted into XY Z coordinate system, and then you see the spatial distribution of the star cluster, young star cluster. Here I have drawn the star cluster younger than 700 million year in the color format, and rest of them are gray, the older cluster. So, and this is the density heat map of the same thing. Basically both are the same, only that is the density heat map. You can see that there is some structure of the star cluster, and they are close to the spiral arms, but we still don't see clear spiral arms, because we have drawn all the cluster up to 700 million year. So when we draw this in the smaller a scale, so because spiral arms are the place where the star formation takes place, so the young cluster are formed in the spiral arms. So we have just drawn those star clusters which are 0 to 10 million year, 10 to 20 and 20 to 30. So very young star cluster, we have taken the subsample, and we have drawn the same diagram, density heat map. And you can see the top one where the star cluster are drawn in the 0 to 10 million year age range. The spiral arms are clearly visible. So this is the local arm, and particularly the three arms are quite visible here, this local arm and Sagittarius arm and the Perseus arm. So from the young cluster in our sample, we can clearly trace the three spiral arms, and scutum arm is little bit faint, feeble, so we cannot see. But one of the important thing here, we have noticed that as you go from the 10 year to 30 year, you will notice that these spiral arms are leaving, these clusters are leaving from the spiral arms, and they are filling the interarm region. So we concluded that most of the cluster are formed in the spiral arms, and within 10 to 15 years, they start leaving the spiral arm and fill the interarm region. In fact, it is believed that more than 90% of the cluster are already destroyed. Only 10% of the cluster are survive in the spiral arms. So we have determined the rotational speed of the spiral arms and found that the rotational speed, I mean, as a function of galactic eccentric distance, is decreasing. So it means different spiral arms have different rotational speed around the galactic center. Normally in density wave theory we assume that all have the same velocity, same rotational speed, but from the spiral arms, from the cluster sample, it is found that they have the different speed, and it was further confirmed by the recent study by Liu et al. And they also found the similar distribution where the the rotational speed around the galactic center of the spiral arms is decreasing. So different spiral arms have different speeds. So basically this tells about the transient nature of the star cluster. So I just 5 minutes. So we, as I have shown, that 40% star clusters are distributed in northern hemisphere, 60% are distributed in southern hemisphere. It means it is not uniformly distributed. So there is a plane which is actually below our galactic plane, around which the star clusters are equally distributed. So we try to find this plane, and then we draw the distribution here of the star cluster, and we found that this is the exponential decay. So here we determine the scale height and found that most of the star cluster, I mean 1 upon E of the total value peak. So there is 60%, 63% star cluster are confined in 90 parsec region, very, very inner disk. So this is called thin disk. So most of the star clusters are found in the galactic thin disk, and then as they become older, they evolve and they fill the thick disk region. And of course, this Z is dependent upon the whether you are looking towards the galactic center or you are looking the galactic anti-center direction. Of course, if these are young cluster, you will see these cluster towards the galactic plane, and as they become older, you will see they are drifting away, so their scale height will be larger. So I will skip this one. So this diagram, again I am coming back. So in this picture you can see here we have the factor Z0, which tell you there is offset around which you have the equal number of star cluster. So if you push your plane below by 17 parsec, which we have determined in this study, so you will find that you have the star cluster above and below the same number. So what does it mean that star cluster defined by the galactic cluster, this galactic plane defined by the star cluster, is actually 17 parsec below our galactic disk, what we call a galactic disk, or B equal to 0 or Z equal to 0. So we have the galactic disk, but actual plane defined by the star cluster is below. So this is called solar offset. So actual plane, so the position of our sun in the galactic disk is actually the 17 parsec above this galactic plane defined with star cluster. Say it is not just using the star cluster, but it is seen in the other planet population, stellar population distribution like OB stars, Cepheids, star forming regions, molecular clouds, that all these planes are below our today's galactic disk, and sun is almost 17 parsec above these planes defined by various stellar population. So this is called solar offset, and because sun is rotating around the center of galaxy, so this plane is in sinusoidal manner revolving around them. So it is going up and down in a ripple manner, and over a period of time this solar offset will reduce and go 0, and then again will become negative, so because it is moving in the circular fashion around the galactic center. So one of the things we have done, because we had the reddening information or extension information of the star cluster, we have tried to see the distribution of this extension, because extension tells about the dust and gas in the galactic plane. So we have tried to see the distribution, and you see here most of the dust and gas is lying in the galactic center direction, as you see here. So this is the anti-center direction 180, and this is the galactic center direction 0 and 360. So this is the galactic. So you see here that in terms of density you see high value, and towards galactic center most of the dust and gas lies where the star formation is taking place and the star cluster are forming. While in the anti-center direction there is not much dust and gas, so not much star cluster are forming in this direction. So of course we have seen this in the diagram, and this is varying in the sinusoidal fashion. And what we have seen in the vertical direction also, this reddening is varying linearly. So as you go up, this reddening is varying slowly, and even in the down direction it is varying. So you will see this kind of variation. So one of the things we have noticed this metallicity distribution of the star cluster, and there are very small sample, 1879 cluster, among them 600 plus star cluster spectroscopic observation metallicity, and rest for 1200 photometric observation metallicity. So we try to see the age metallicity relation. Of course, there is a lot of scattering, but we found that okay, up to 240 million year means this young regime where you have the constant metallicity slope, there is zero metallicity slope, close to zero, and then you have a decay in metallicity slope. It means the metallicity is decreasing after 240 million years. So it tells that okay, how the star formation is taking place. I mean, when they are younger, so there is larger metallicity, and the older star cluster which above the 240 million years, they have the less metallicity and they follow a slope. And in RGC, this radial galactic-centric distance and metallicity thing, you also see the slope with the RGC. So means if you draw this chemical composition of metallicity of this open star cluster up to 12.8 kpc, you will see there is slope, and after that there is no slope. It is almost zero, very close to zero. So it means most of the star formation is happening in the up to the 12.8 kiloparsec, and in the outer region beyond the 12.8 kiloparsec, we don't see any star formation happening in this direction. So now, almost second last slide, we have done all this work using a sample of few thousand of star clusters. Sometimes we have taken 6,000 star cluster, but for the metallicity of less number of star cluster. But still having these large samples, whether our cluster sample is complete or not. As I have already shown the spatial distribution, star clusters are basically confined. Still, having the Gaia, we have not detected all the star clusters so far. And in one of the recent study in Murera et al., 2025, they have found that okay, this densities of the star cluster is decreasing. Otherwise, it should be uniformly distributed if there is complete. It is complete, but that is not happening. What does it mean that star cluster sample is not complete as yet? And we have more than 6,000 star cluster, but still we expect more than 1 lakh star cluster. So in future, things may be better because you will have the Rubin Observatory in the southern hemisphere. I mean, they are going very deep, and they will have the proper motion up to 24 magnitude. So we will have a many stars from this survey, and we expect many star cluster, particularly in southern areas. And future, in fact, Gaia NIR is proposed. So because star cluster are basically in the dusty region. So if you have the NIR observation, you can even penetrate up to large distance, and you can observe many more star clusters. So hopefully in future, this statistic will be more complete, and you can do this kind of work with larger sample of data. Yeah, thank you very much.
Thank you, Yogesh, for a very exciting talk. Now the session is open for a few questions. Yeah.
Hello, sir. Thank you for the nice talk. Sir, can you please go back to that slide where you put the age against that
So age.
distance from the galactic plane. Sir, when it showed that when the cluster ages, it goes out of the plane.
Where did it? Okay. Yeah. Yeah.
Yes, I want to just understand that, sir, the black points, I understand that they are the point. And what are these, sir, blue points which make work?
See, this is the distribution of clusters in the age and jet plane. Jet plane means above the galactic plane we have determined the jet, how far it is from the galactic plane. Basically, jet equal to d sine b. So we have drawn this. So what we have done in small segment of the age, we have calculated the mean of jet. Okay. So we just to see how this is varying, because particularly towards larger age range, there are many clusters, and they are scattered. But good number of clusters are away from the galactic plane. So just to see the trend, how it is varying, so we have determined the mean value of the Z, and we can see that up to almost 800 million year or 700 million year. So this is almost constant. So all these young and intermediate star clusters are very confined still in the galactic plane, very close to the galactic plane. Okay, of course, towards the galactic center they are more confined. In anti-center direction they are a bit scattered, but still up to 700 million years they are very close to the galactic plane. But with these older clusters, they leave the galactic disk because there are encounters in the galactic disk among the star cluster, among the star forming regions, as well as due to the tidal interaction, all these things. So they leave that region, and once they are away from the galactic disk, they are safe. I mean, because their life is more. So here they will not survive for longer period, but when they go away, so their survival chance will be better. So that is reflected here, and from 700 million year above, so the Z is increasing. This tells that okay, the older star clusters are away from the galactic disk.
Sir, one more question I have, sir. There was one more slide that contains the proper motion of the star. So it goes to the starting slide.
Okay.
Yes, sir. So this one. So here, there we can see two stars, sir, which have and simultaneously two directional proper motions in the right image.
Yeah.
Sir, why the same one?
See what happens. We assume this when we didn't have this proper motion information. So we assume this as a star cluster, single star cluster. And all the bright stars are the member of the star cluster because we didn't have any other information, no parallax, no proper motion, nothing, right? Just you see the image and you tell, okay, this is the star cluster. That the kind of work we used to earlier. But now we have the Gaia information where the parallax and proper motion is there. So now we know that okay, even in this central region there are bright stars, but they are not part of the cluster because they are either foreground star mostly because they are bright, or even they can be the background star also. Of course, background star will be fainter, then they really need to be very bright to be in the picture. So either they are background or the foreground field star. They are not part of the cluster. Okay, because all these cluster who are part of the cluster, all these stars which are part of the cluster are at the same distance, right? So this tells that without the proper motion information, you cannot tell whether the star which is in the very close to the central region of the cluster is part of the actually the cluster or not.
Yeah, maybe can you take the question?
Sure, sure.
During the break. What is it?
Just one curious thing about this solar offset. I see a large number now. I know in earlier 90s or something like 5 or 6%, but do you see any systematic increase in the solar offset?
It will not happen. It will change. It will change because it is evolution process. It is going in the sinusoidal direction. So it will change and will increase. But because we are talking about 20, 30 years, right? We are talking about 90s and I'm talking about this 2025. Actually, what happens? It depends on how big sample you have. And then there are different stellar populations also, like OB star we have determined, RLRA, Cepheid for example, different. So people have different solar offset. But what I noticed in one of my studies that this is the data completeness issue. What kind of data you are taking, right? Unless until you have a large sample of data, your error estimation in this solar offset determination is large. As well as the distance scale also. If you are, because in different study, people have used different distance scales. Some are just taking within 1 kiloparsec, OB star within 1 kiloparsec, and some are taking up to even 3 kiloparsec, 4 kiloparsec. So it is distance driven also, as well as the data completeness. So right now, more or less, in one of the recent studies, they have compiled solar offset for last maybe 30, 40 years, and they have given a value of something like 16.8 parsec. So that is the value.
So next up, so you are assigning cluster membership based on proper bias promotion, right?
Yeah.
So have you considered differential reddening for the individual stars in a single cluster?
Yeah, this is a very good question. Actually, differential reddening is important in the very young star cluster, right? So differential reddening is also important when you have the color diagram and you determine the extension value from that color diagram. So differential extension, you know, pollute your fitting, right? Here, what we are doing right now, we already know the cluster member because cluster member are known from the parallax information, proper motion, right? So cluster member are already known. So even your color diagram is polluted, but you have the cluster member nicely, and you can determine the reddening, even in the differential reddening thing. Of course, in a young star cluster, within the star cluster, you will have the reddening vary from one place to other place. That you can study because it will give you the mean reddening color diagram, and then from the mean reddening, you can individually check each star and see what is the shift from that mean reddening, and then you can calculate the reddening in this region, right?
And what is your take on Gaia's proper motion being a reliable source for the small Magellanic cloud and the large Magellanic cloud? Especially, I'm talking in terms of proper motion being a reliable source of information for the individual stars in a star cluster.
See, star clusters are identified from the Gaia data, right? We have the Gaia data and we have the Gaia proper motion and parallax. So this is a subset because we have the large number of stars. We are trying to identify your clumpy structure. Wherever there is clumpy structure, we identify this cluster and having this Gaia information, parallax and proper motion. So it will work for every region, whichever Gaia has object, whether it is Magellanic cloud, whether it is northern hemisphere, southern hemisphere, it is same for everything, right? There is no change because we are using the proper motion parallax to identify the motion of the star, whether they are in the same direction, and the distance, whether they are at the same distance. So from this information, we are saying that this is the cluster because they have the similar proper motion and similar parallax.
But can Gaia disentangle two stars in the small Magellanic cloud star cluster?
See, of course, it has limitations. I mean, future because that spatial resolution it will improve in the future. Not all the two stars will be resolved, right? So that limitation will always be there because star cluster they may be very very close also. So in that case, it will contaminate your magnitude information, proper motion, parallax, and all this. Yeah.
Maybe in the interest of time, we will take the rest of the questions during the break.
Okay.
Thank you once again, Yogesh, for a wonderful talk. And I hope there is an announcement by Joshi.
A couple of announcements. First of all, tea will be served in front of this auditorium. Second, I request all the participants returning back while the airport kindly confirm their travel on the registration desk just in front of the auditorium.